Good evening, everybody. Let's get started. This will be the review session for the Jan round of the USACO contest, the silver level. Some of you may have taken this past round. The results actually would be better than the December round. At least the first two questions, most people feel, yeah, that's not too bad. Actually, the feeling is similar to the silver level, but the feeling to the gold level is different. This round, the gold level is harder. Actually, the gold level passing threshold is 650, much lower than the typical 750. So depends. Some students feel Jan round is harder, and some students think Jan round is easier. So depending on individual situation, also depending on your mode, some students got better prepared in terms of the energy, in terms of the warming up. So if you prepare better, then you feel better and you do better. There is still 2 more rounds in February and also in March. So the purpose for such review sessions would be to help you in the next 2 rounds, especially for those who are eager to find out what we can do to better solve the questions, even though our pace may not have picked up. So I'm going to go through the questions here. Yes, the recording would be posted. Actually, the video files would be stored at Zoom, and you're going to get the link as you have received the announcement. Okay. All right, so let's get started here. The first question, that's for the Soulmates. Refresh your memory here. The Soulmates, you're going to have 2 numbers. Each number can go up to 10 to the power of 18. You're going to find out the number of the steps, the minimum number of the steps. You're going to bring the 2 numbers to the same. The operations you can do is you can multiply by 2, divided by 2, and also adding by 1. So for this one, 31 to 13, you can, this one does not make sense to multiply this by 2, right? So I'm going to say this is the P, okay, I'm going to use this one for A, and this is B here. So A is bigger. So I'm going to try to divide by 2. That makes more sense, right? But here, this one is odd. So I'm going to add 1. So make it 32. So that's 1 operation already. Divided by 2, that'll be 16. So another 1 here. Now 16 and 13, this one still is bigger. I'm going to do this one divided by 2. So that's the 3rd time. 8 is big than, it's less than 13. So can we do times 2? No, that will go back to 16, right? And you can add by 1. How many times you're going to do that one? You're going to add by 5 times, right? 8 to 13, add 5 times, and plus the 3 steps we have taken so far. So that will give us 8. Actually, that is the best. 5 more times. So 1, 1, 1, 3, that's 8. You may think I can divide by 2, so make it 4 and plus 2. Why plus 2? Because I'm going to make it 6 and plus 1 here. So plus 5, plus 1, that's 6, and then times 2, that's 12, and then plus 1 here. So that is also 1, 2, 3, 4, 5. So that's also a 5 plus the 3, that's 8. Okay, so this probably makes more sense, right? You can figure it out. And some during the contest, right, try to figure out why 997 to 120, this will take 21. Okay, you cannot go down. You can only times 2 divided by 2 and plus 1. Cannot add by 1. So the same mechanism. This number is bigger than this one. So suppose that's A, that's B, right? A is bigger than B. So it makes more sense to bring down the big number. So plus 1, that's 998. Divided by 2, that's 449 here. This one is still bigger than this number. So I'm going to add 1. So 450 divided by 2, 250. 250 is still bigger than this number. I'm going to divide it by 2 here. So 125 still is bigger. I mean, added by 1, 126 divided by 2, 63. Now, this number is bigger than this number. And B is bigger than A here. I have done so far, right? 1, 2, 3, 4, 5, 6, 7 times already to reach. So that's my new A, that's my new B. How do you go from here? Well, you don't want to multiply by 2. You don't want to plus by 1. If you do plus 1, how many times are you going to go? That's much bigger than the 20, right? So probably that's not the best way to do. Okay, so probably I can do this one here. I'm going to divide this number by 2. So my goal is I'm going to use the 63 to reach the 60. Once I can reach 60, and I'm going to divide by 2 times 2. Hope this will make, oh, okay, a lot of messages. Sorry, I did not see it. Oh, you're right. I'm sorry. You're right. Let me change. So this is 499, right? 997, 998. That's 499 here, and make it. Oh, my mistake. Thank you. How could I make this a mistake? Thank you. And then that's right. Thank you. Okay, so notice here, this is an important observation here. From here, 63 to 120, I'm kind of lost what to do, right? Because I don't want to add by 1, that would take 57 times. I don't want to multiply by 1, multiply by 2, that will go back to 126. So, right, work backward from 120. So this is the idea, right? I'm going to divide this 120 by 2. Hopefully later, if I can reach 60 from 63, I'll just times 2 to get back to 120. Okay, so this will count also one more step, right? So now going from 63 to 60, I know this number is bigger than this one, so there's no other way, right? Just bring this number down, but to bring down, I have to plus 1. So 64 here, divided by 2, 32. This number and this number, right? This one is bigger. Again, I'm going to divide it by 2. This is bigger than this one here, so divide by 2 here. This one is bigger, divided by 2 here. And this one is bigger. Well, maybe, well, I can keep going, right? So this one is 8 and this is 4. Probably would be the same. Does not make any difference. If you can minus 1, that would be better, right? I can go from 8 to 7, but you cannot minus 1. So divided by 2, 4, and plus 3. So I'm going to do 5, 6. Okay, so let's count. That's the original. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, yeah, there's one more time here. So I need to get one more time here. So 7 cannot go to 15. Next time at times 2, that's the one, right? But I'm going to plus 1 here. Yeah, okay, that makes sense. So that's 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total 20 steps. You're right, Justin, that's correct. Okay, now I see Dylan's suggestion, very good. Yu Yan's suggestion, good. Justin, Bill, Tom, very good. Okay, thank you guys. Okay, hope this gives us the hint. The idea is I can bring down the number as much as I can until they're very close. Okay, so if A is bigger than B, I'm going to bring down A. If B is bigger than A, I'm going to bring down B. But before I bring down, I need to take a right. If this number is even, that's fine, just divide by 2. If this number is odd, I'm going to add one extra step from the side of B. Okay. Here you go. Okay, so from the side of B here, I can do subtraction because that corresponds to, I'm going to multiply 2 and plus 1 here. But from A, I cannot bring down by 1. Okay, for me to bring down A, if even it is odd, I have to plus 1 first and then bring down, divide by 2. Okay, so that's the idea. Try to bring down the numbers, make it smaller and smaller. You say, how come I can, well, how fast or how efficient I can go until I have the number small enough? Well, actually, it is not too big. It is not too bad. So let me show the number of steps required. Is this DP? Actually, it is not DP. This is the divide and conquer. You can see here, right? So initially, A, B for each one is up to 10 to the power of 18. Each time, either A is bigger than B or B is bigger than A, right? If none of them is true, then A and B are the same, then I'm done, right? So each time, either A is going to shrink by half or may require one more extra step, right? Because for A, I need to plus 1 if it's odd. For B, if it's odd, I need to do minus 1. So anyway, every 2 steps, I'm going to get either A or B divided by 2. So let's see, if a number you start from up to 1018, if you want to divide by 2, right, at most 2 steps, I'm going to shrink the number by 2. So going from 10 to the power of 18, how many times, if you keep dividing by 2, right, how many times this number will make it up to, say, 1 here? Or constant, right? A small number that is small enough, say 2, 3, I can see the answer. Okay, this actually, H is not too big. So basically, right, this is 10 to the power of 18, roughly the same as 2 to the power of H. That means H is roughly taking the log of 10 to the power of 18 with base 2. And don't think this number is huge, right? This number itself is huge, but if you take the logarithm, this one is actually not too big. This is about 60. So you're going to do at most 60 times to bring down the number, right, close to about 1. As I said, right, sometimes we may have, we may take 2 times to divide by 2, right? If A is odd, you're going to plus 1 divided by 2, plus 1 divided by 2. Okay, so that will take 120 steps at most to bring down A to a number almost like 1. The same for B, another 120 times. So total will take about 240 steps. That's not bad at all. So this will give us an idea of recursion. And we have done recursion in the 4th semester. So maybe other techniques we have not covered, but this one we have covered. So let me clear this part. We have done recursion in unit 10 in the 4th semester. All right, so here we try to implement the idea, bring the big number down. Don't try to make the number, make the smaller number bigger, because it would be equivalent, right? If this 63 is less than 120, don't make this number bigger. That will not help us. Actually bring the big number down. That's better. All right, so that's the idea. And we're going to implement this one recursively. All right, so let's see. I'm going to just go through one implementation, and you're going to see this actually is not too bad. Okay, so the Soulmate. Here, since if it's just one sub-test case, this kind of seems to be too weak, right? Who made the question? Anyway, it would take just too less time to compute. So actually this says we're going to do 10 pairs. Actually, even this n goes much bigger, still we can finish this, right? As we just saw, each pair will take about 240 steps to bring down to the constant level, say 1 or 2. So even n can go to 1,000 or even 10,000. This one still will work. Okay, so let's see here. N, that's number of the sub-test cases. While n is positive, we're going to process two numbers, a and b. Make sure you're going to read them in long integers, because it says, right, they could go up to 10 to the power of 18. So don't make the mistake. If you do that one, you're going to read the wrong numbers. And of course, the answer would not be correct. And we're going to just call this one solve AB. And normally, right, if you have a function that is recursive, you have to have a helper function here. You cannot make main recursive. Anyway, so this is the part I'm going to solve for AB. Basically, we want to find out the minimum number of steps to bring AB to the same value. If A and B are the same, that's the base case, then you return 0 because you don't need any extra step to bring them equal. They're already equal. Okay, now we're going to process or handle the three cases. A is bigger than B. A is actually less than B over 2. And actually, oh, I've done this one in a interesting step. Okay, you can see here. So if A is bigger than B, of course, I'm going to bring A down. So if A is odd, we'll just divide it by 2 here, and that's one extra step. But if A is odd, you're going to add 1 to A, and then the number of the extra steps, right, will be, actually, this would be 1 here. If A is odd, extra would be 1. If A is even, extra would be 0. So depending on the situation, to find out the value, find out the solution, AB would be the same as A over 2 and B plus 1 or plus 2, depending on the parity of A, right? If I can get the solution here, this is actually A over 2, right? With this plus the extra steps, I can get the original AB. This is the A over 2. Okay, so that is when A is bigger than B. Or maybe this one is confusing. I'm going to do this one here. So A over 2. That makes sense, more sense, right? If I get the value of the pair A and B plus the extra steps, then I would get the answer for A and B. Okay, so that is when A is bigger than B, easy to go. If A is less than B over 2, less than or equal to, now this makes more sense. I'm going to bring B down. Okay, again, if B is odd, I'm going to minus 1 from B, and then extra step would be 1. Otherwise, I'm going to just do B over 2. Okay, so this makes sense. Even b divided by 2 still is bigger than a. You, of course, you're going to do this one here. Now the third scenario, a is bigger than b, else a is less than or equal to b. Now if a is also less than or equal to b over 2, the rest, otherwise what's left would be this one here. B should be big, a should be bigger than b over 2, but less than or equal to b, cannot be equal. If a is equal, it's handled here. Bigger than b is handled here. Less than or equal to b over 2 is handled here. So what's left would be this one here. Exactly. A is bigger than b over 2, but less than b. So what we're going to do, we're going to check the difference. Now the difference is b minus a. So we're going to add d steps to b, right? If this number is good, we're going to do this one. Otherwise, we're going to divide both a and b. Oh, that's better. I have b over 2 here, a over 2. So here, if a is odd, we're going to add 1 to a, and extra will increase by 1. If b is odd, we're going to minus 1 from b, and extra will increase by 1. Now we're going to solve this a over 2 and b over 2. And with the extra 2 plus here extra, this one is referring to this plus 1, this extra referring to this minus 1, and then the 2 referring to the divided by 2. So I'm going to compare this number against d. So that's the direct addition, right? I'm going to add a to d, add a and d here, so that will give me b. Or I'm going to do this one, a over 2 and b over 2, and hopefully this will be better. If it's not, then we're going to do the d. Actually, there's one test case, this one here, the 10 and 24. So this 10 and the 24, that's a here, that's b here. So you don't want to add 1 here. That will add 14 times, right? That's too big. But you can add 1 here and add another 1 here and times 2. So 3 steps would make the two numbers the same. But using our argument here, so 10 is less than 24. So I'm going to do, okay, 10 and 24 divided by 2. This time, right, a is actually less than, here, a is less than or equal to b over 2. This is 24, 12 here, 10. So that's one step. And then I'm going to do the divided by 2, or I'm going to have the difference here. The difference d is 2 plus the 1, that'll be 3. But if I have this 5 and 6, that's already 2. Okay. Divided by 2 once, divided by 2 once, right? And a plus here. So that'll be 1 step here, one here, that'll be 3 steps. So it's this time, if I add directly, it's better. Then I bring down this a divided by 2, b divided by 2. So I'm going to check the 2. Sometimes this would be more, the cost would be higher. Sometimes this would be higher. Depends, right? Like the one we had, say 63 to 120. You don't want to go directly. This d is too big. Then we would just divide by 2. Okay, so hope this is helpful. Okay, just want to make sure during the contest, how did you do this one? How long did it take you to figure out? Yeah, this is actually, you don't want to go one by one. That would be too tedious. And of course, that will go out of time. If you figured out this would be recursive, and always try to bring the numbers down rather than make it bigger, then this question would be easy, right? You can pretty much, you can finish within 40 minutes or at most 1 hour. Good. Okay, so if you have any question, right, feel free to raise it. And also if you have, some smart observation, also I can raise it so we can all share. Already? Okay, that's for this one. The second question. Theoretically, we also have done this. Okay, this one, you can use a structure to solve this one. We're going to use a stack to solve this problem. Okay, so let's review this problem, refresh. We have an array of size n. N could go up to 10, 5. Okay, actually 300,000, not just 100,000. Okay, so clearly n squared does not work. If your algorithm has complexity big O n squared, it does not work. So h1 through hn, each number is in the range actually from 1 through n, not from 1 through a million or a billion. So actually it would be, oh, actually this is a permutation, I'm sorry, is it? Yeah, okay, so h is a permutation of the numbers, so actually all of them are distinct. Okay, life actually is easier. Okay, this one does not matter. If the numbers, there are duplicates, you can still solve it. Okay, don't worry. Okay, so let's see here how we can come up with a good idea to solve this problem. Right, so don't feel frustrated. Okay, if you do have this experience, right, I got so frightened. Whenever I see a question like this one, I got panic. Okay. Exactly. So Bill, right? So some questions may be easier to you, but harder to others. And some questions may be easy to others and hard to you. Yeah, okay. So you just need to practice. If a technique or a trick, right? If you do it once, the first time you see it, it's new and kind of shocking. But if you have done it, you have seen it, right? Half a dozen times, or even say 10 times, then it becomes a routine. Well, the reason I did for the first question, right, to bring down that would just make sure you're going to do the recursion, not exponential growth. You don't want to have this this case, right? You want to do fn here and end it inside here, right? You're going to do f, say n minus 1, and you're going to do, say, n minus 3. This will be bad because 1 calls for 2, 2 calls for 4, 4 calls for 8. That will just go through exponential growth. Then life becomes hard. Notice what we did, right? Every time it will just call it once. So that will make life much easier. And every time we're going to bring down to 2. So that's how you reduce the number of the function calls and avoid the exponential growth. Okay, don't worry, we're going to have more units. Actually, we're going to come back for recursion. Do we? Yeah, probably in the units, the 22, 23, and also actually for unit 17, we're going to do a lot of recursion for the DFS. DFS is implemented mainly using recursion, so you're going to have a lot of chances to do so. Okay, so let's go back to this one here, the array H. We're going to find out the pairs of the cows at position I and J if and only if if the numbers between, so this is hi here, this is hj, all of them actually would be lower than this, the smaller one of the two. So hi is here and hj is here. All the numbers actually would be lower than this smaller one. No. So all the numbers between hi and hj, they would be no more, they would be actually strictly lower than this one. So they can only go like this. Or if you want, right, you can also, it is equivalent to say all the numbers actually, right, the vertical bars are actually, no, that's wrong, I'm sorry, still would be this one here. So it should be less than this dotted line, not the trapezoid. Trapezoid is wrong because you might have numbers bigger than this one here, less than the taller one, but bigger than the lower one. That's not allowed here. Okay. So we're going to find out all the pairs I and j, so that I less than j, and we're going to add j minus I plus 1, basically, right, the number of points between I and j. J minus I would be the length, plus 1, that would be the number of the points, and add them together. So this one, you don't have to get a max value or minimum value, but you're going to add all these pairs together. As I mentioned earlier, right, you can't do the n squared. So one way to do this one, the brute force, I'm going to try all the pairs. I goes from 1 through n, j goes from I plus 1 through n. If all the values between I and j, they would be less than the smaller one of the two, then I'm going to add that quantity. So that would be inefficient. And how many cases you can pass? You can pass the first 3 cases when n is less than 5,000, because you can do n squared. And provided you can do the the max value between I and j in a smart way. Actually, it's not too bad. Every time you fix I and move j, and every time you're going to increase j, you're going to have a new value and make sure this value is less than the smaller number between the two. Okay, so this one, yeah, if your complexity is n log n, should be able to finish. Okay, there may be something, well, okay, yeah, you're right. Well, to be honest, actually, it's not a big deal. So here, n log m, if n is 3 times 10, 5, log n is less than 20, right? Because log 1 million is about 20. So this one is about 6 million. Okay, so this is actually much less than the threshold 10.9. So if you do Java, this will take roughly, right, about 1 second, about 1 second, because we're going to add, yeah, the the time for input and also to write the output. Actually, output does not take much time, just one number, but input you can read 300,000 integers. Okay, so if you claim, right, your true algorithm, the complexity truly is n log n, you should be able to finish even using Python. Okay, so actually, probably does not make any difference if you use Python for bronze, but starting from silver, I seldom see, people using Python, because anyway, Python still is not fast enough, unless USACO specifies, right? Say the time for Java would be twice about of the C++, and then Python would be again twice amount of time as Java. Then that would be fair. Now, Java and Python would have the same amount of time, then that's kind of unfair. Why doesn't USACO support Python? Because IOI does not support Python yet. That's true. Mm-hmm. Yeah, Pascal is such an old language. Actually, I was surprised it was still there years ago. But Python would actually, in a few years, might be added to the official, the commonly used language. I would not be surprised at all. That's different. Websites support Python does not mean we can use it to do the CP, competitive programming. Still, you don't do a lot of the Python, especially the part that requires a lot of intensive calculation, because Python still is slow. Just like Java is actually not used for a lot of the CP. Oh, okay. Still, it's different, right? For a lot of the core, you still use C and C++ because it is, compared to Java, it's a lower level language. So if it is lower, then it is faster. Yeah. Okay, so let's still go back to this part here. How do you find out the pairs ij so that will satisfy the restriction? That means all the numbers between I and j, they would be strictly lower than the smaller one of hi and hj. I don't want to do all of them one by one, but I want to get the sum. This is normally the trick. You can have the brute force way, go through each pair, each individual, and get the total sum. But also, if you take a different viewpoint, a different this angle, then you can get the sum, but you don't have to go through each individual pair. So this one, how do you find out? Okay, so let's analyze. Still keep this diagram here, and I'm going to show how we can do better. Okay, if you want to do this one, so pretty much you're going to do something like this. This is your hi, and this is your hj. As long as all the numbers in between that are smaller, then you can do it. More here, right? Suppose I'm going to find out a minimum value here, and then going down here, I hope this is monotonic decreasing. And to the right of this minimum value, I'm going to see this one monotonically increasing. And here we have seen all the numbers are distinct, right? Because H is a permutation. Okay, so let's not talk about the language anyway. For USACO, language is not important because we never use any of the fancy features. Basically, we use the very fundamental program flow. Plus the data structures, yeah, that's all we need. Nothing for, say, OOP, right? Nothing for graphics, nothing for interaction, for the database, and so on, right? None of them. Okay, anyway, so this would be a good way to get started. So I'm going to find out, start from this one, right? If the next number start from hi here, if this one is less than hi, keep going until I start to see numbers going bigger. And then if this trend does not continue, say after this hj, right, it will go down again. Then I'm going to say, be happy to see here. Then I'm going to say on the left of this minimum value, any value here and any value here, they would make a good pair. Okay, hope this is making sense. Even though this is not the right way to solve the question, but it is a good starting point. actually a student tried to explain this idea. I thought, yeah, this actually makes a lot of sense, but still does not work. Okay, so maybe you have some similar ideas or experience, but how do you, in a timely manner, fix your idea or try to guide you through either by your instinct, by the experience, or whatever, right? Or just say the inside in your mind tells you, okay, Jack, go this way. All right, so here it is good if you can find out a minimum value here and then count, right, to the left, how many points here, to the right, how many points. So each one of them. So suppose you have, say, X points to the left, Y points to the right. Each of this X points, right, can be paired with any of the values on the right. Okay, that's very nice. So looks like you're going to find out or decompose the whole H array here into the segments. And then you're going to do this process each segment individually. Okay, think about it. This one actually is not working. Why? I was actually impressed by this idea. Try to partition this array, right, from 0 through n-1 into the segments like this one. First going down and then come up, going down and come up. And actually for the sample case, let's do the sample case here, 4, 3, 1, 2, 5, 6, 7. That's exactly the pattern. You're going to go down first, one that's the lowest point, and then coming up. Okay. All right. If you have not noticed, right, actually, what about, okay, this one actually does not matter. But what if I have something like this here? This point I and this point J, that works. You're right. Yeah. Good. Okay. Yeah, Yuan has observed, right? So this one should be a valid pair because all the values between would be less than this I and less than this J. Or you can say this is I2 and this is J2. So this J and this one, right, they could form the pairs here, but they can also form pairs like this. And this will make life much harder. So how do you keep track of the values here? How do you keep track? This is a local maximum. This is another local maximum. So for the point of this one here, this does not work. This works. So you can never pair this I versus this J2. And if you switch the order, right? If this I is taller than this J, then yes, you can. So kind of hard. How do you keep track of the high points and also the relative positions? Okay, after drawing this diagram, maybe it's helpful to you for you to come up with a modification, and then from here you can have a working idea to solve this problem. Okay, I'm going to use this diagram to illustrate how I would come up with a working idea. Notice, right, when I have this HI and later I have this HJ here, this is invisible to HJ2 here. Why? Because this one is taller than this one, right? So for this J2 can never see this HI. So for this purpose, I guess I'm going to say, hey, this one, I'm going to assume that you don't exist. Okay, so that means I might save a value like this one here, I2, and save a value here, and all the values less than HJ here, I'm going to ignore them, or kind of, I would need them when I process. Actually, when I was at position I here, these numbers actually would help, right? Because they could be paired with HI. But when I have processed this one here again, right? So HJ is taller than HI, and then these numbers lower than HI, they would not make any use for the HJ here. The same thing, HJ is taller than HI here. When I process J2, actually, I would not be able to see this at all, right? I would not have this I and J2 because there is a number that is taller in the middle. Okay, I think I understand Wenda's idea, right? Actually, there is a structure. You can do so, find out the max value of a subarray that is faster than big O(n). Actually, we do have a structure specifically to answer such a question. And we're going to do that one in the gold level. That is called a range query structure. It's called a segment tree. But we don't need such a segment tree to solve this question. You're going to see how we can arrive at a solution. Actually, this one, we have done a similar question when we talked about in Unit 5, we have done questions like this. Okay, if you sort, of course, right after you sort spanning n log n time, and then you can do the minimal max. That you're right, that'll be true. But here, after you sort, then you're going to mess up with the calculation, right? J minus I. Okay, at least I don't know how to, I can sort them. Maybe you can still remember the positions, and then how do you, without sorting. Well, without sorting, if you want to find the max value, you cannot do in O1 time. The best we can do in log n time. Okay, so the trick here is I'm going to use a stack. I'm going to use a stack. Okay. When I am working with this branch here, when I go through this one, right, this number is less than this one, I'm going to push this one to the stack. This one is smaller, push this to the stack until I'm at the lowest point here, pushed all the numbers here. Now, when I begin to come up here, when I see a number that is bigger than this one here, I'm going to remove the number from the stack. So in the stack, I only have the numbers that will go down. That means if the number is in the stack, all the rest of the numbers in the stack, they would be bigger than this one. Okay, but before I remove them, I should be able to, like this HI here, right? When I am here, this one actually can form a pair, right? This one, even though it is less than this I, can also form a pair until this one is bigger, then I cannot still, the first one bigger than HI, I can still do, but the next one I can't. Right? This, the first value that is bigger than this number, I am going to add to the stack, right? This one I can still form a pair, but not the next one. So anyway, when I'm considering such a value, all the values in the stack, they should be bigger than or equal to this one. Cannot be equal. They should be bigger than this one here. So I'm going to remove all those values that are less than this one here. Whenever I remove them, I'm going to find out whether it's possible to form a pair. Okay, when you go like this one here, you can't, right? Or actually, when you process this value here, these numbers, they cannot all exist, because when you do this one here, right, this one is already less than this one. So when you add this number to the stack, this one is already gone. When you process this one here, this is in, then this is gone. So when you have this number, the one right before this HI, this is bigger, and I'm going to say remove this one here and try to bring this. Okay, but before I do this one, when this number was the last one or at the top of the stack, right, the next number must be bigger than this one. So I'm going to say this one and this one, they can form a pair. And then we're going to remove this one here and then add the contribution of this pair to the total count and try the next one. If this one is still less than this one, we're going to see the next part and still add the contribution until this one is bigger than, and then just add the contribution and then don't remove it. And then we're going to push this HI into the stack. So when I push the value HI to the stack, all the numbers that are below this HI would be removed. So only this I would be added here. So you have this value, this value, this value here, and then this. The same thing here. When you add this, when you're on the path going down, all the values will be added in and no contribution to the total count, j minus I plus 1. Only when you're in the path going up, then you may have the contribution, because, right, only this and this would have the pair. When you're going down, you don't. Okay, so we're going to have a stack to work on this. Now, does it remind you the stack has been used? Okay, so here's stack. We have done something like this one, balance the parentheses. You can see, right, given a string, and you process from the left to right, and you want to see whether they're matched, something that is similar. You're right, it is a monotonic stack, because if the value is less, right, this one is in the last number in the stack and this one is bigger, I'm going to say, before I push this one into the stack, I'm going to remove this one. So all the numbers will just be monotonically decreasing. All right, so let me take a little break here and you can think about it. When we come back, we're going to continue and showing how a working idea can be derived. All right, so 5 minutes break. All right, let's come back. So to do the counting, j minus I plus 1 here, every time I have the j here, I need to find out the I so that can form a pair. So observe, right? If you have a value here, then this actually cannot work. If this one, even though it is bigger than the lowest value, if you have a value here, then does not work, right? All the values lower than this one here cannot form a pair with HJ. The same thing, right? If you have value here, then all the values lower than this one cannot be formed like this one here. So that works perfect, right? When I process this one here, all the values lower than this one have been removed from the stack. If this J is bigger than this one here, right? All the values actually lower than this one, you don't have a chance to form a pair with HJ. Only those bigger than this one would be eligible to form a pair, right? That's exactly when this was in the stack, all the values in the stack will be bigger than this one. Now, if this HJ is going to go taller than this one here, okay, we're going to try in the stack how many values are bigger than this one here until the values, right, I keep processing and then they are bigger than HJ, then I'm going to stop. So as Alan pointed out, actually, I'm going to have a monotonic stack. So notice this one, I don't want to go the IJ, the interval. This time, I just focus on the right-hand side. The left-hand side I would be processed here. All the elements will be added to the stack at most once. Sometimes you may not be able to add it because like this lowest point, right, you don't even have a chance to, well, actually you might, okay. Even the lowest point would have the chance to be added to the stack, but next time it will be removed immediately. So every element would be added to the stack once and will be removed once. Okay, so even though we're going to do a lot of insertion and removal or pushing and also popping, but still the complexity would be big O(n). So here, to find out the total count, it would take just O(n) time rather than the big O(n) squared. Actually, if you do the big O(n) squared, you have to do a smart way. Otherwise, you may have to do big O(n) cubed. Okay, so maybe still not so clear, but I'm going to show you the code, and then you can see, yeah, this actually is not too bad. Okay, I guarantee you can have that impression. Okay, so I think I still have this one in Java, and then the next one I'm going to show you in C++. All right, n, that's the number of the integers. H, that's the input array, and I'm going to read this one. That's easy. Okay, now I'm going to have a stack. The stack with the pairs. Okay, why I need the pairs? Because I need the value and also need the position. Right, as I just put it here, I need the value compared with this one, and also I need to know where it was, right? And then when I do the this one form pair with this one, I need to find out j minus whom plus 1, right? So I need to have that piece of information. So here I'm going to have a helper class. The pair would have the value and also the position. Okay, this one is purely for the purpose of bundle the data together. I could have the stack of one stack of the value and another stack of the position. And then the two stacks will go the same way. When I push a value, and then both stacks will be pushed a value. If I pop, then both stacks will pop a value. So you can do that too. So if you don't want to have a helper array, you can have two stacks. Or you're going to push the value first and push the position. Either way, it's fine. Okay, so first we're going to do the answer that is 2 times n minus 1y, because two adjacent numbers always would be a good one, right? From I to I plus 1. There's nothing between them, so they could form a pair satisfying the restriction, or they can play frisbee. Okay, so this one is so far so good. Now I'm going to do the rest here. process each number in order. Okay, I don't sort, but I'm going to process them from the left to right. If the stack is empty, or if this HJ value is less than the value at the top of the stack. So here you're going to do the peak. Stack.peak will just retrieve the value, but don't remove it from the stack. The stack contains the pairs, right? So each pair, we're going to have the value. So if the HJ is less than the value at the top of the stack, or the first element of the stack, now no choice, right? If HJ is less than, or if this stack is empty, so you have nothing else to do but to add this one to the stack. So we're going to push this new pair with value HJ and then position J to the stack. So that's the easy situation. At least right when J is 0, you're going to do this. Okay, else, as long as the stack is not empty, we do have elements in the stack. Now, if HJ is bigger than the top value of the stack, okay, so if, okay, I'm going to use the, that's the stack, even though kind of, if you do the stack, right, actually stack would be more likely you're going to do like this one. Like this, right? That's a stack. But now I'm going to say, because we're going to keep track of the positions. So this is at the top of the stack, and then HJ is here. Put HJ here. So this is my HJ here. It is bigger than the top of the stack. Okay. So itself cannot form a pair, but the one right before this here, so that's position size -1 here. This is size -2. So if I do have a value here, then I can form a pair. This one is the smallest one. That's at the top of the stack. This would be the second one here. If you want to do the position, this actually would be the position size -2. So I'm going to form this pair, J minus this. So this would be J minus this is the position, right? Remember the entry right before this lowest value, or the top of this one. Top is the peak. This one, the size -2 here. J minus this I plus 1. That's the contribution of these this pair. Now, if this one size is big, then size is bigger than 1 here. If it's 1, then you cannot do it. Okay. After having added this the contribution, now I'm going to remove this value. So pop, we're going to remove this one here. Now, if I still have this pattern, right? So HJ is still bigger than this one, the next iteration, the new peak, now it's this one here. HJ still is bigger than this one. I still have the next one that is bigger than this. Then I'm going to add the contribution of this pair. So this would be the new peak. That's the second, the new size -2 here. So that's the contribution J minus this new I plus 1. Now, until if HJ is bigger than this one, if it's bigger than this one, then you're going to do. Otherwise, if HJ is not bigger than this one, we're going to stop. Right? There is no way you're going to form another one. So if this one is HJ is less than this top of the new stack, the new top of the stack, then there's no way you can do this one, but this is the value in the middle, right? If you want to form inside this pair, but the value in the middle is bigger than this HJ, then that's invalid. That's not a good pair. So I'm going to stop. So whenever HJ is less than the top of the stack, we're going to stop. And then we're going to push this HJ to the new, to the stack. So this one becomes the new top of the stack. Notice, right? When we stop, the condition is HJ is less than the value here. And then we're going to add this one to, well, this a little bit Okay, maybe move this one here, right? So when we add, it will be here, and then this value is above it. Okay, so far we still maintain the stack would be monotonically decreasing. Okay, notice, right? Every value here, you're going to push HJ and the pair, right? HJJ, push it once, and you're going to pop it out once. Well, for stack, you cannot reuse it. Once it's popped out, it's gone. So here, even though we do have 1 layer, 2 layers, right? But the complexity still would be big O N. The argument is simple. A value could be added in twice, and the value can only be popped out once. So actually, you can say this is not just 1 n, but 2 n times. That's okay. So that's still big O N. And then when you're done, when you have finished all of them, the answer would be the total value, and then make this one long, because it is possible the value may be too big. So each one is not big, because you know, right, j minus I plus 1, this is guaranteed to be in the range of integer, but you can change it to make it bigger. So I mean, this answer may go out of range of integer, so make this one long. All right, so the code again, right, is not complicated. 51 lines of code, including the comments. So it is not too bad. Okay, so hope this can give you some hint for future problems like this one. All right, any question, comment? No, good. Okay, so let's go to the next question. That would be question 3. Okay, question 3 is clean. Many students. I don't know the result, because for gold and platinum, you can see how you doing. But for bronze and silver, now the number of participants, it's too big, so they're not going to provide the information anymore. Before, the silver was also displayed. So I'm pretty sure for question 3, most students had trouble. So this is a question, a continuation from a previous question, serial, also made by Drew. So this is serial 2. Basically, we have n cows here, and we have m types of the cereal. You can say the cereal boxes, m of them. The rule to distribute the boxes would be, if the first choice of cow is available, then take the first choice. If the first choice is gone, but the second choice is still there, then take the second choice. If none of them is there, then the cow will go hungry without any box. So in the serial 1, which was in March 2020, the US Open round, you were asked if the cows go actually back order. So you can have the cows. So these are the first, second choices for the cows, right? You add the cows from the back. For each time you add a cow, find out how many cows would have a box. So the output would be actually n numbers. So this time the question has changed. It does not give you the order of the cows taking the boxes. Actually, you're responsible to find out a way so that the number of cows taking boxes would be maximum, or the number of cows go hungry without boxes would be minimum. And also you're going to show one order of the cows taking the boxes, so that will result to the minimum number of cows go hungry. Okay, so it is hard. Actually, this one and also the question 3 in the gold level both have this one here. If the answer is not unique, anyone would be fine. So that question also killed a lot of enthusiasm. So this one also, actually, if you want to check whether your answer is correct, besides submitting to your server, if you want to do it on your own, you have to check this one. So suppose you say, right, cow 3, cow 1, cow 4, and cow 5, and so on. So we're going to apply the rule. If the first choice is there, take that. If the first one is not available, but the second one is there, take the second one. Otherwise, this cow would go empty-handed. So you're going to just basically check this rule one by one and find out how many cows have in boxes or how many cows have no boxes, and check whether that will agree with this. So actually, it is not so easy to solve this one. So if this one was bothering you, it's reasonably fine. Or we can say, oh yeah, I could not solve this one. Okay, so this one you have to, you know what? Let's take the sample case. Actually, it's worth the effort to spend here. Notice this one in the description. It also says, since the first 3 cows and the last 5 cows, they don't share any of the boxes, right? The first 3 cows would only be interested in the first 4 boxes, and then the next 5 cows would be interested in the next how many cows boxes from 5 to 8, 4, right? 5, 6, 7. Oh, actually 5. So the next 5 cows, 5 boxes. So they can be processed independently. The first 3 cows and then the last 5 cows, they are independent. So from this observation, you know the answer cannot be unique, right? You can say put the first 3 cows first, and then do the second group, or do the second group and then do the first group. And also you can mix the order. So a lot of the choices to have the valid order, so that they will all end up with the maximum number of cows with boxes. Here, Dylan's suggestion, representing the cow's favorite cereals graphically. Very good. Okay, let's talk about it in a moment, but first let's look at the sample. The sample input here, the 3 cows, 2, 1, 3, 4, 2, 3 here. Okay, there is a slight difference. If you take, say, cow 1 takes box 2, cow 2 takes box 3, then cow 3 has nothing to do, right? Because cow 2 is gone. When cow 2 takes 3, then box 3 is gone. Even though there are boxes 1 and 4, but cow 3 does not like it neither. So only 2 cows would have the boxes, and then that's not the best. Easily, right? You can see, change the order. We can make this outcome better. So that's cow 1 here. We can do cow 1 here first, but then we're going to do cow 3 next. Okay, the box 2 is gone. Then cow 3 cannot take box 2, but she can take box 3. Right, now box 3 is gone, then cow 2 can take box 4. So there is a difference. So here you only have 2 cows having boxes. Here you can have 3 cows having the boxes. Okay, now let's come back to Dylan's suggestion. Where do I get started? And after some thinking, you can wonder, how do I represent the serial choices, first one, second one here, in a graph or graphically? It is a question how you represent the information here, first choice, second choice, right? In a way that will help us to work with. So far, it looks like out of nowhere. Okay, Dylan's suggestion, right? You can have a graph where the vertices are the serials, edges are the preferences. Okay, how do you represent the preferences? Do you think it would be the same if you swap the first and the second of the cows? That's a good question, Ray. Actually, I'm not sure how to answer this question. Would it be the same? I don't know how to prove it. Or if I want to say this is not the same, but how do I give a count example? Would it be the same? My guess is actually should be the same, but I need to prove that is the case. But my feeling is should be correct, Raymond's suggestion. Okay, Dylan also said directed graph. Okay, how do you make this directed graph? Okay, we are getting there. We're getting there. Actually, both Dylan's suggestion and also Raymond's comment, right? Actually, we are getting there. We need to represent the information in a useful or meaningful data structure so that we can work on it. So far, seems to be hard. Okay, so for this one, it is actually important. You need to represent the information in a graph, as Dylan said. Okay, also Anthony's suggestion, both would be good. Okay, so this is actually, I don't know how long it took you guys to come up with the idea. So you have the serial, the boxes, right? So this one, box 2, there's an edge going from 2 to 1. As Dylan said, right, we're going to have the directed graph. And we're going to have 3 to 4. And then you have 2 to 3 here, right? 2 to 1, 2 to 3, and 3 to 1. Okay, the reason is if you have taken this call 2 here, I mean this box 2 here, now call 1 becomes available. Okay, of course you say, right, what if box one is somewhere else? That's fine. But if a box one is not the first choice, right? Otherwise, you cannot have the box one. You have to finish box two, then you can do one. And of course, right, you cannot use this call one. If call one takes box two, and then, well, if call one, it appears some other places, right, that's fine. So you have to use some other cow take two, and then one would be available. So naturally, you're going to have an edge going from this first choice to the second choice. So actually, we're going to make it a little bit more, right? So here, each box, we're going to build an edge. So we're going to say that's cow one here. So each cow actually is an edge. Each cow is an edge from her first choice to her second choice. 2 to 3, that's cow 2 here. Actually, that's cow 3 here. And 3 to 4, that's cow 2. So Anthony's point, right? So every vertex in the graph is actually a cereal box. Every edge is actually a cow. Right? I may not have an edge from 2 to 4 because I don't have a cow whose first choice is 2, second choice is 4. So with such a graph, what can I do? Okay, first I'm going to find out the disjoint components. Okay, when I say this one, some of you say, no, I don't know what you're talking about. It is true. And actually, we're going to do this one. Actually, unit 13, that's binary search. Unit 14, that's the prefix sum and the suffix sum, which is, somebody has raised this point, right, in question 2. Okay, we're going to do that one. And then the next part, float fill, we're going to do the components. So hopefully we're going to finish the float fill before the fab round. And then we're going to spend a lot of time doing the graph representation. So we're going to do the graph, and in graph traversal BFS, the breadth first search, and also going to do the graph traversal depth first search DFS. So actually, we should start the spring semester a little bit earlier. And actually, that's our policy for next calendar year. Our design is try to start earlier, and then for each USACO contest weekend, right, we're going, the school will take a break, so you have more time to prepare for the contest. But we're going to start maybe 2 weeks earlier. Okay, that can help you. And also, we have made during the break, you guys are working hard. We're also working hard to adapt to the increased difficulty level. Actually, for silver class, we have made make it to 3 levels: silver 1, silver 2, and silver 3. The same for gold 1, 2, 3. I mean, for bronze 1, 2, 3, and gold. Actually, we're going to make it a 2-year class because now it is getting harder and harder to land for the promotion. So you have to work hard and also work smartly. All right, okay. So for component, okay, when I say component, would be all the nodes are connected. If you have a graph, you say that is component, then the nodes here, they're connected. But different components, they're disjoint. Okay, they may be connected like this one here, that's fine. Okay, this is also fine. Okay, they may have cycles, they may not have cycles, does not matter. But each component will contain all the elements inside, right? They are connected. So you can say these are the disjoint, the maximum disjoint components. That means this component is maximum. In a sense, if you add one more 9 here, it will be disjoint. If you add any one more node here, it will become disconnected. So this is the maximum disjoint components. Okay, so we're going to do the traversal BFS or DFS, or we're going to do the flood fill, find out the components. You know, this could be unfair because we have not done this one. We're going to talk about using the techniques, right, to solve questions. Okay, anyway, I'm going to just address the idea, and then eventually I'm going to just show you the code, and then hopefully in 2-3 weeks, right, you're going to get more comfortable. And then by then, looking back at the code, is yeah, okay, this does make sense. Maybe so far it's still not that clear, or does not make much sense, or the more we learn, the more we talk about, you get more confused. That's perfectly fine, right? That's actually the way you learn. You're gonna at the beginning, right, you're confused, and then after a while you say, okay, yeah, I think I understand it better now. Right before you feel happy, then you say, oops, now it's getting harder and more confusing. That's true. You have to go through the cycles, confusing, clear, and then go through multiple cycles, and eventually you can, yeah, okay, that makes sense. Okay, so we're going to find out the components like this one here. Actually, this part, cow 1, 2, 3, and then the boxes 1, 2, 3, 4 will form a component. The cow 5, cow 4 through cow 8, and then the boxes 5 through 8 will also form a component because they're disjoint. Now we're going to work on each one independently. As I said, right, actually you can, in terms of the number of cows go hungry, that's independent, because no matter what you do, you're going to find out the minimum number of cows go in the hungry. But the order actually would be very flexible. Anyway, so it does not require to produce a order that either say next go, graphically smallest one, or any other restrictions. So here, anyone is fine. So we're going to say for each one, we're going to decide how many cows will go hungry. And we're going to pick one particular order so that will yield the minimum number of cows go hungry. Okay, so we're going to talk about this one using the jargon that is common in compute. I mean, the graph, not computer graphics, the graph theory. Okay, so the idea is if you have a component, the number of the edges, that's E, the number of the vertices, okay, if this V and E are related by this one here, the number of edges is one less than the number of the vertices, then you know this is called a tree. We've done the trees, didn't we? Let me check here. Yes, we've done this. Perfect. Okay. So if you have a component that is connected, the number of the edges is one less than the number of the vertices, then this is tree. Okay, a tree is good. Could it be like this one? And could it be like this one here? And trees are good. Why? You can pick a root. Once you have the root, every new edge corresponds to a new node. That's why, right? After picking this root here, edge, node, edge, node, edge, node. That's why the number of the edges here should be one less than the number of the nodes or the vertices. Okay, good. So we're going to do this one. If you have a tree that is connected, right? Trees, of course, will be connected. Why? Because every node will be connected to the root. You have X here and a Y here, right? Just find the path from X to root, find the path from Y to root, and then glue them together, then that will be path from X to Y. All right, so if you have such a tree, as we just noticed, right, the vertices would be the number of the cereal boxes, and an E, the edges, right, would be the number of cows. There are more boxes than the cows. Then actually you can every cow would get a box. Actually, you can start from the root, just to go down here and pick. So actually we can ignore the direction of the edges, the first, the second, right? Because any edge, either from first choice to second choice or second choice to first choice, anyway, for each one, just pick the one you go first. So start from the root, actually go anywhere. You can start from any node as the root, just to go down and assign a box to a tree, to a cow, right? If this is first choice, the second one, then I'm going to say assign this one to the cow. And if this one is the second, this one is first choice, right? Assign this one to the cow. You still have the choice to assign a cereal box to each cow. So here, in this case, no cow would go hungry if it is a tree structure. Okay. The second scenario, E and V would be the same. Okay, it is connected, and number of edges is the same as number of the vertices. How can this be? Well, it must be the case. There is an edge, you introduce a new edge, but does not introduce a new node, right? So here you have a new edge, but you don't introduce a new node. So in this case, E and V would be the same. Okay, so this is actually still easy to handle. Why? Just to pick. So this edge, right? One of them must be the first choice for a count, right? So we're going to say pick this. So suppose this one is first choice. I'm going to pick this one here as root. Now I'm going to say, suppose this one is gone. Actually, mistake. Suppose this node is gone, then two edges will be gone also. The rest still would be number of the vertices and number of the edges, right? Will satisfy this restriction. Why? Because edges would go down by 2, right? If I remove this vertex, this edge is gone, this edge is gone. And then V would -1. So now the new E and the new V still satisfy the restriction. So that would be the first scenario. Okay, so now we do have, so when you have, okay, let me go back to the scenario. E is bigger than V here. That means edges are the cows. V versus, right, that would be the boxes. Okay, you know things are going ugly. There are more cows than the boxes, then you know for sure some cows would go hungry, right? At least E minus V cows would go hungry. And actually you can prove that actually is, you're right. So when E is V, no cows. So in both cases, this one, no hungry, no hungry. But when E is bigger than V, then you know E minus V number of cows would go hungry. Okay, how do you do this one? You can find out we call a spanning tree. Okay, spanning tree is basically you have a graph. You may have a lot of the edges. Okay, maybe this one is connected here, maybe this one is connected here, or maybe there's another here. So it is a graph, but you're going to pick certain edges. So it will take all the nodes and also will form a tree. So that's called a spanning tree. And in Go level, we're going to talk about this one, the minimal spanning tree, which is used frequently. Okay, so we're going to find out a spanning tree. Again, this could be, the choice could be arbitrary. The typical way is you're going to use DFS to generate a spanning tree. Okay, using what we did, right? We're going to take all the vertices and we're going to do the tree. How many edges here? So should have v minus 1 edges. So the rest, e minus this. So this would be e minus v plus 1 here. Okay, pick one of these cows, right? The edges, remember, each edge corresponds to a 1 cow here. So for one of the cows here, not in the v minus 1 edges of this spanning tree. So take any one of them and remove it. And then the rest, the tree, it's guaranteed you're going to have all the cows will have a box plus the 1 here. Okay, you're going to go through the more detailed analysis. But anyway, the idea is pick one of them, remove it, the rest would be fine. And then the E minus V cows would go hungry. We said, right, at least E minus V cows will go hungry. But we have shown one way, exactly E minus V cows will go hungry. So for each component, these with E edges, V vertices would be E minus V cows go hungry. Well, when E is less than V minus, when E is less than V, then you don't. When E is equal, that's not. So you can have the max 0 and this one. That's the contribution to the total hungry cows. And then you're going to have a more detailed analysis to find out which cows you need to get first to start. Basically, if you don't have a cycle, perfect, that will be a tree. If you do have a cycle, well, if the E is equal to V or E is bigger than V, then you know there must be a cycle in the graph. So find out a node in the cycle, start from there, and you can let the cows take the boxes one by one. And then that will guarantee there will be the maximum number of cows getting the boxes. So I can go through some of the, okay, one version here, and you can see how this one is done. I'm going to show here the this version actually is a modification of the answer in the USACO website. Actually, it's similar to a solution to one of the students. Actually, it's a very smart idea. You're going to have a helper class. That's the edge here. You can have the cow ID, right? Each edge corresponds to a cow, and you have the from the first to the second one. So actually, this one you're going to make it both directions. So you're going to say from the first choice to the second choice, and then that is the true node. Is it the first choice or not? So if you go from first choice to second choice, then this one is false. Going from the second one to the first one, then the true would be the first choice, then this is first is true. Okay, that's the constructor, that empty default constructor. That's if you give me the values for the cow and then true, and then whether it is the first choice for the true node, just take this typical one, assign them to the corresponding variables. N and M would be the number of the cows and also the number of the boxes. ADJ, that would be the adjacency information. For each serial box, we're going to assign or associate a list, or in this case, a vector. A vector would be the same as a array list in Java. We're going to associate a list or a vector of the edges here. Edge is defined here. In Java, we don't allow the it's still allowed, but it's discouraged to have a vector or an array of vectors or array lists. So you're going to see this list of array lists. And then these would be the typical we're going to use for the traversal to indicate whether a node has been visited when trying to find out cycle, or you're going to find out a component. And then this will be used to indicate whether a cow would get a cereal. And here, the number of cows would be at most 100,000, but the number of the boxes would be at most 200,000. So here the difference. Notice the difference, right? Bool is the same as boolean in Java. The number of cows going hungry started from 0 here. This is a queue. This would be the same as we will always do, right? Array deck. We have said if you do that in Java, array deck is preferred because it does not do the synchronization. But in C++, we don't have that structure. So this queue actually would handle the synchronization. This is the order of the cows taking the boxes. So this actually would be used at the end. When you print the result, you're going to do this one. Order, you can always pop from the front, and then also you can add to the other side. So first in, first out, last in, last out. This is to help us to find out the first serial. Where do you start? And this one is ignore edge, right? If you have a cow, this is to start from a cycle. You pick one cow, and then later don't go back to that cow again. So ignore that one. This is to find out cycle. You start from the current one, from the previous one here. We're going to do this a lot. Find a cycle. This one is recursive, right? So find a cycle here, and then we'll do find a cycle here. If the next one, so this is the adjacency information. That means there is an edge going from current serial box to the next one here. The next is an edge. So next dot 2 would be the 2 box. The next dot cow ID, that would be this cow that will have the first and the second choices for this edge. So if this one has been visited, that means you have found a cycle. Well, the cycle would be a little bit tricky here because for each one we have added the edge here, right? Say every time we have the first choice A, second choice B, we're going to add this edge. That's the cow ID, one based from A to B here. And then this is not, B is not the first choice, but we're going to also add from B to A. A is the first choice. So actually, we're going to have 2 edges for every cow here. Okay, cow A and cow box A and a box B here. There's an edge this way here. There's an edge going this way here. So by itself, actually, it will form a cycle. But this cycle is not what we have here, the cycle. So next should not be the previous one. So don't say, okay, A, the next is B, but B is, you can say next 2, right? It will go back to A. That's not a cycle. Okay, so if we do find a cycle, we're going to say, okay, this next cow would be to be ignored for the future traversal. And you say, okay, this cow would be the first one to be processed or take the cereal boxes. And mark this one, yeah, this cow would get a box. And then once you have found one such cow, you don't have to find the cycle anymore. So start from this cow, and we're going to, like this one here. Once we find a cycle here, if the first serial box, right, is not -1, so by default, this will be -1 here. If it's not -1, that means we have found a cycle, and then do this one here and start from there. Otherwise, you don't have a cycle, then we just say start from this box I. So both cases, we're going to find out the maximum number of the cows that will go, that will get a box. Okay, every time when we do this one, we're going to assign if a cow has not been visited in the current one, and we're going to find a, give the cow a box and push this to the order and process the next one until you cannot find out the next count. Basically, we're going to do this one using the DFS to find out the spanning tree and assign the serial boxes to the counts when we visit them in order. So at the end, some counts have boxes, some counts don't have boxes. For those that don't have boxes, we're going to say, hey, increase the number of cows go hungry, and then put these cows in order, right? Those cows with boxes would go first, and these cows without boxes, they would go at the end. At the end, when this all done, we're going to print the information. First, that's the number of cows would go hungry, and then print one order. So this is one of the many choices of the cows taking boxes so that the number of cows go hungry would be minimum. Actually, it will be interesting to find out how many ways are there so that the number of cows go hungry, right, would be minimum. So that would be a question for gold. And I'm not sure whether next time Drew will make this into the contest. But if that's the case, I'm pretty sure not just we are considering, maybe somebody also would be saying, okay, we can do this one. But who knows? There was a question, I think, modern art was first raised, I think, 2016, the season. And then in season 2021, the same similar question appeared again. So that means after some time, it could still appear. So I would suggest, right, after you have done the graph traversal BFS, DFS, plot fill, and look back at the question, see whether you can rework on the problem, and also think further. If the question changes a little bit, rather than having one such order, report how many different orders there are so that number of the cows go hungry would be minimum. Okay, actually, I just thought about this one. I did not realize this could be a question that is too hard to solve. Just like a lot of questions in computer science, if they are NP hard, then you cannot find out the answer in the polynomial time. So NP hard actually sometimes would be as hard as, say, exponential, or even harder, say, factorial. And for USACO purpose, right, normally we only consider, say, at most n squared when n is not too big. Normally when n is 10.5 in the magnitude, right, you cannot even think of n squared. The best, right, would be n log n, or sometimes n squared log n. So NP normally would not appear at all. So you can do n log n, that's fine. And sometimes this could appear. This one still is fine, right? So 10.5 here, this one is less than 20, and squared, that would be 4 times 10 to the power 7. That's still less than 10.9. So this probably, that would be the highest that we can tolerate. Make it even harder. I mean, higher than that will very likely will go out of the range, right? If you multiply this by 20, then this would be 8 times 10, 8. That's very close to 10, 9 already. So normally this is highest. So I'm just thinking, right, saying, and you can think about this question later. Even though it's not easy to find it out, maybe there's no answer, but it's not, it's worth the effort to think about it. All right. Okay. So for those of you who have tried, very good effort. And then we still have 2 more rounds for season 2022. So we're going to do our best to help you guys. During the spring semester, we're going to put more effort on hands-on experience. So we're going to assign less questions. Before we would say each unit we're going to have, say, 7, 8 questions. We're going to maybe cover 2 or 3, and then the rest would all be your homework. Probably that's not realistic. I know you guys are busy. So in the spring semester, starting next week, we're going to give you maybe 2 questions per week, but we would ask you to work on them and also submit. So that will make it easier for you to have more hands-on experience, not like, okay, go into the contest, worked so hard for 3 hours, 4 hours, and only solved 1 question. That means you did not practice enough. You need to practice more. So please, in the spring semester and also the subsequent training, right? Please help us to help you, and we'll try our best to help you guys. All right. Okay. That's all for this review session, and looking forward to see you guys next week. All right. Okay. Bye.